In this lecture, we will study theory for the topic 12.4 and 12.5, which is curvilinear motion of particles. Okay, so let's say that a particle is traveling through this curved path. Instead of going on a rectilinear motion, which is a straight line motion, now particle is going through curvature. Now this particle can be a car going through this curved road, or it can be a boat going through a river. So let's identify some important points along this path. So there is point A, point B, point C, point D, and point E. Now, how do we measure the position, velocity, and acceleration of particle when it's going through this curved path? So for that, we need a reference point or origin. If the motion of the particle is in 2 dimensions, then we use XY coordinate system. Or if it is 3 dimensions, then we use X, Y, and Z coordinate system, where X-axis, XY is this plane, which is this screen here, and Z-axis is perpendicular to this plane and coming out from the plane. And we can define the position of the particle at each location using a position vector R that defines the X, Y, and Z coordinates for that point, and we can write that position vector as certain value X times I plus Y times J plus Z times K, where X, Y, and Z are the coordinates of that point. So if position vector is written for A, we can say that this is XA, YA, ZA, where XA, YA, and ZA are X, Y, and Z location of point A, and where I, J, K are unit vectors. So this is what statics has covered. What is position vector and how to find it. And if we need to find the exact distance of that point from the origin O, then we need to find the magnitude of this vector, which is square root of XA square plus YA square plus ZA square. So vector has both magnitude and direction. So this is vector and this is the magnitude of the vector. Now, how about the velocity at the curved path? So velocity at the curved path is actually tangent to the path. So this is the velocity vector at A. At point B, velocity is tangent to the curvature and points in the direction of motion. So this is B and this is velocity of B. At C, again, it's tangent to the path and points in the direction of motion. So this is velocity of C, this is velocity of D, and finally, this is velocity of E. So velocity vector, you can see here that this is tangent to all the points and it's passing through that curvature. So remember this concept about position and velocity for curvilinear path. Now let's look at the presentation. So objective is describe the motion of a particle traveling along a curved path and relate kinematic quantities in terms of rectangular components of the vector. So in this example, a plane is going in the air in X, Y, Z motion. So it has a 3-dimension motion. It's moving in XY plane, plus it's also going up in the Z axis. So motion of the plane can be tracked using radar by defining the XYZ coordinates of the plane recorded as a function of time. How can we determine the velocity and acceleration of the plane at the given instant? We can define that velocity and acceleration of the plane at the given instant if we know how X, Y, and Z coordinates of the position of the plane changes relative to time. So we need to know the X coordinate as a function of time, Y coordinate as a function of time, and Z coordinate as a function of time, and we can individually find the X, Y, Z location of the plane relative to origin. So let's say we define that the origin is here, X, Y, and Z again is perpendicular to X, Y, then at any given instant we can define the position of plane using X, Y, Z coordinates. And if we know how X, Y, and Z change as a function of time, we can write the position vector for plane R, which is xt multiplied by unit vector yt multiplied by unit vector j, which is in y direction, and zt multiplied by unit vector k, where I, j, k define the direction and x, y, z define the magnitude for the position. And once we have this vector, we can easily find velocity v as a vector by taking the derivative of each one of this relative to time. So this is like dx by dt I, dy by dt j, and dz by dt. Okay. And in the same fashion, we can calculate acceleration by taking one more derivative of velocity, which is dv by dt. So acceleration can be calculated by taking individual components derivative and writing that as a vector. So there are a couple of more examples, such as the roller coaster car travels along a fixed helical path at a constant speed, and the coordinate system is defined here. This is the origin 0, 0 point. This is x-axis, this is y-axis, and this is z-axis. At any given point, the position of the car can be defined using x, y, z location. So how can we determine the position and acceleration? So once we find the position, we can take the derivative to find velocity and acceleration. But why is it important to predict the acceleration of the car? This is very important to predict the acceleration of the car, because as it travels through the spiral slide, it experiences the centrifugal force, and it is important to know that the centrifugal force is within the limit so that the car does not leave the track. And for that, we will apply the equation sum of forces equal to mass times acceleration. And for that, we need acceleration to calculate that force. And acceleration is a kinematic quantity. We can solve using kinematic analysis. Okay, so this is the same plot that I just explained to the notebook, that position can be defined using position vector r, and the velocity is tangent at each point. As you can see, velocity is always perpendicular to the position vector. It's 90 degree and it's tangent to the curvature, and it points in the direction of travel. So in this case, the particle is going from left to right. So this is the direction the particle is traveling right to left. And now how can we calculate the acceleration? So to get the acceleration, what we need to do is, at each point we need to get the velocity, and we need to join these velocity vectors and create a new graph, which is called hodograph. And acceleration is tangent to velocity at hodograph, similar to how velocity is tangent to position. Acceleration is tangent to velocity. Okay. And so now in 3 dimension, for generalized equation, position can be written as combination of x, y, and z component multiplied with corresponding unit vectors, where each x, y, and z can be function of time. And using this equation, we can calculate magnitude for the position vector. We can also calculate the unit vector by dividing the position vector by its magnitude. So in this presentation slides, whenever anything which is red and bold, that means it's vector. Anything that's like plain, that means it's scalar. And velocity is derivative of position, and that's how we get the magnitude of velocity at individual component. And acceleration is derivative of velocity, and that's how we get the acceleration at different points. Now at this point, I would like to introduce a different notation here. So we know that velocity is like derivative of position, dr by dt. Oftentimes we write this as r dot. So r and one dot, which indicates one derivative relative to time. Similar to that, acceleration can be written as dv by dt, or it can also be written as v dot. So anytime when we have one dot on top of a kinematic quantity, that means we are talking about first derivative. But when we have two dots, for example, r double dot, that means it's second derivative, d square r by dt square. So oftentimes we use this notation just to simplify the equation. So as you can see here, acceleration is v dot or x double dot. So acceleration is first derivative of velocity or the second derivative of position. Okay, and now there are some problems where either velocity is given as a function of time, or the position is given as a function, y position is given as a function of x position, and we need to calculate the velocity of the particle or the acceleration of the particle. So you can see here that y dot is like first derivative, y double dot is second derivative, so that's velocity and acceleration, and that's how they are being calculated.